Let's see if I hopefully don't put yourself to sleep. It's so good to be here, even if I'm all the way here in Singapore. I really wish that I could go to Sri Lanka one day. But for now, I think this is the best that we can do. Once things open up, I really hope to see you all face to face one day. And if you ever swing by to Singapore, I'd be more than happy to host you as well. So for this talk, I'd like to share with you some of the challenges that we run into as a company, actually, and that's how we sort of started to think about, how we can use software engineering analytics to improve the productivity of our software engineering team, and also improve the engagement, the happiness of our team, and hopefully, as a whole, we are able to create long-term value in the entire software engineering industry. So let me jump right into it. This talk will be composed of two parts. First, we will talk about the problem that we run into, and then the solution that we did to approach the problem. And of course, there could be variant solutions out there. I'll share with you one example of how we did it. In the Q&A, we can also figure out how we can discuss further any issues and any nuances that may come up. So first, a brief background about Hubble. We are a construction tech company. So we manage the end-to-end construction life cycle. And because it's construction in general, it's a very, very complex industry as a whole. So eventually, when you come up with a company that solves problems in construction, you have to scale. In 2019, the size of the Hubble engineering team is somewhere about perhaps 5 people, 10 people. It's somewhere there. So it's very easy for us to actually see, who's being productive, who's not being productive, why are they not productive, so on and so forth. Because with a very, very lean team, you can actually see how each person is performing. There's not a lot of communication gaps. And so it's very easy to coordinate, to collaborate. However, as a thriving company, we eventually grew to a size where we could no longer sustain being able to monitor and actually help our engineers become more productive or unblock the things that are slowing them down. We actually grew from somewhere between 5 to 10 engineers to today we have about 35 engineers in the whole company. So now we became an organization where you have managers of managers, and now it becomes more nuanced on how we can actually find out what's going on and how we can help the team. The good thing about the problem that we're trying to solve is that, as our previous speakers have mentioned, there's a lot of data. Data is replete. We can actually use a lot of data that so that it can help us make decisions. And I hope in this talk you can also use some of these along the way. As many of you might know, and I'm pretty sure almost all of you are using Git. In Hubble, we are also using a version of Git. We are using an implementation of Git called GitLab, but of course, this entire solution you can also use if you're using Bitbucket, if you're using GitHub. So what I'm going to share with you is how we use data from Git to actually help analyze how we can solve problems in our team. So here's a common problem that I run into actually as a VP of engineering. It's very important for me to keep the team engaged. There was a research that was done in 2013 whereby they found that a highly engaged team actually outperforms their competitors by as much as 147%. What that means is that for every one person, for every one engineer, I'm getting a bonus headcount of another engineer and another half an engineer, 147%. So because of that, right, I'm getting all those resources for free. I'm getting all those productivity for free. And all I have to do is to help my engineer be happy, feel that they belong to the company, they belong to the team, they are valued, and their contributions are celebrated. So it's very important for me to think about this because it's good for the company, it's good for the person. There was a research that was done by Microsoft, which was presented a couple of years ago in Wharton, whereby they found that 20% of overtime per week actually leads to 1.6 times higher disengagement. So it's very important for me as their boss to have a reasonable amount of overtime so that we don't burn out the engineers. This is real data that you're seeing here on the right. So what we did was we try to calculate the total number of commits, the total number of activities that they do in our repository within work hours and outside work hours. What we are able to do then is that we are able to create a ratio or a percentage. So if you look at the purple line, you can see that we have grown 2 years ago to somewhere around 7.5% over time on the average to somewhere around 15%. In a typical startup, it can be argued that you don't sleep, the startup is a baby, yada yada. But really, it's not helpful at all. People will burn out, and it's going to be bad for the company if we continue with the trajectory that we are going. In a typical scenario, without software engineering analytics, all we hear about are we hear this information from 101. We don't have a quantitative solutions to this. But now with this kind of information, I can straight away go to HR, go to our chief product officer, go to our CEO and say, hey, people are burning out and we shouldn't keep this going. And because it will negatively impact the business if people burn out, right? People will leave, people will not be as productive, yada yada. So it's actually for the benefit of the company to help people have good physical and mental health. So with this kind of data, we are actually able to measure what's the health of our engineering team to a large extent. Here's another problem that I run into very often. How do I protect the company from knowledge decay? Think about it. All of us are in many ways mercenaries, right? We join a company, we work for a few years, and then we leave. We do the same thing over and over again in multiple companies that we go through along the way. And every time we leave a company, we actually leave a lot of knowledge with us. And the rest of the team actually don't know about them. So you probably have run into those scenarios whereby people will come into or will call you and then they'll be like, hey, can you help us around this item or that item because we don't have knowledge about this. This is also happening, everywhere else. In the software engineering industry, you probably have heard of this uh, term called the bus factor, which is sort of like a joke, whereby the idea is that how many engineers has to be run over by a bus for the project to fail. Because if all the engineers leave, of course nobody knows about the project. Then you have to rewrite. It's very expensive. Yada yada. So here's a way that we try to analyze the bus factor or the potential knowledge decay in our team. If you look at the one with the green box right there, the one on the top, you see John, Cheryl, and Sandy each having several thousand commits. So we compute the total number of commits each person did in a particular project and try to evaluate, how dangerous the project is. If you look at the one on the green box, you can actually see that the distance between their commits is not too bad actually. So the amount of shared knowledge that they have is likely very, very high. So even if John or Cheryl or Sandy, even if one of them leaves the company, there are still two others who can sandbag the damage of one leaving, which means that the project is fine, right? They have a lot of shared knowledge, things are great. But if you look at project number 4 there, the one with the brown box, you can see that Dawson has more than 2,500 commits. But then you can see Pradeep and Vishal has somewhere around 300, right? You can see a significant knowledge gap between Dawson and the two others. Uh, Without software engineering analytics, there's actually no way for me to know this. But now I can actually see that Dawson, because Dawson is significantly more advanced in terms of his knowledge compared to Pradeep and Vishal. Now, if I want to manage that project, I can go to Dawson and say, Dawson, instead of you taking the work for yourself, you can actually distribute it to Pradeep and Vishal. Then you can think about more scalable things that would help the project. Whereas for Pradeep and Vishal, they can actually gain the knowledge and catch up. This will eventually help protect that project in the event that Dawson leaves the company. There's another one. If you look at the bottom one, which is the one with Enrique, Carl, and Pragati. Now, project number 5 is in a very dangerous state because Enrique and Carl has already left the company. And now we are left with Pragati, who if she leave as well, there's nobody else to take over, which means that project number 5 is in grave danger, right? If nobody knows about the project, we have to throw someone in, they will have to relearn, and that will be very, very expensive because if you're trying to learn something, you're not writing code, right? So now that I know that, we are only left with Pragati in that project, and there's a huge danger for the company if Pragati leaves, then I can start to think, maybe I can bring in Mark, maybe I can bring in a few people from other projects to join Pragati. Number one, so that she doesn't burn out. Number two, to protect the company, right? So we need to have that amount of buzz factor. We need to have more engineers to sandbag this kind of scenario, so that if Pragati falls sick, she wants to take a rest day and stuff like that, then we are able to provide her that luxury. Here's another one. I also think about how fast are we delivering our products, right? In an ideal scenario, if you come up with a certain feature, you want your, how should I say, customers to enjoy the benefit of your product as soon as they can, right? So I really think about it a lot, and definitely a lot of CTOs, a lot of VP of engineering think about that as well. So here's what you can do. You can create a value stream analytics. In a typical software development delivery lifecycle, what happens is that you write your code, you commit, and then once you commit enough times, you're happy with your set of commits, then you create a pull request, right? Or in GitHub or in GitLab, it's called a merge request. So you have a bunch of commit, you create a pull request, somebody comes in and review your code. Once they're happy with your code, then they merge it to develop, or they merge it to master, depending on your branching strategy. But eventually, they will have to merge it somewhere, and it takes some time between a merge code to for it to actually be deployed to production. So again, you can see the stages there: your first commit, your pull request, the pull request getting merged, and the merge code to be deployed to production. So it's important then for me to track all those stages, so that in the event that there's a slowdown in one of those steps, I can actually monitor and I can go and solve the problem for my team. So what you're seeing here on the right is that there seems to be a growing amount of time for the time it takes for a pull request to be merged. As you can see, the yellow shade, as it goes from left to right, from earlier to today, it's growing, right? Which is not good. So without software engineering analytics, there's actually no way for me to see this. I will complain, perhaps the product managers will complain, perhaps the engineers will complain, but there's no concrete quantitative way for us to actually see, oh, this is exactly what's going on and we have to address it. With this information, now I can say, oh, it seems that the pull request to merge time is getting longer and longer. What's going on? Are people burning out? Is there a holiday? Are we lacking people? Is it because there's a lot of bugs? Now I can ask all those questions, so that we can go there and solve the problem and make things faster. If we don't know the problem, then there's no way for us to solve it. Here's another one that I think about very often. How do we reduce defect density? Right, this is very important. Of course, for the customer, the more bugs they run into, the less happy they are. The QA team doesn't like bugs. The product managers doesn't like bugs. Of course, for engineers, we don't like bugs as well, right? It hurts our ego. It hurts our feeling if there's a lot of bugs, right? So we want to reduce them. It turns out that there's a research that was done. So Cisco and SmartBear did the research a couple of years ago, and they found that for every commit that you do, the sweet spot in terms of the lines of code per commit is somewhere around 200 to 250. And here's the reason why. Think about it. Suppose I have a pull request and there's like 2,000 lines of code. The reviewer will take a significant amount of time to actually review your code. And because there's a lot of things that comes into play for him to review, it becomes very difficult then to capture issues. So what they found is that as the amount of lines of code increase, the quality of the review decreases. So this is a sweet spot then that they were able to find. So if you have somewhere between 20 to 200 to 250 lines of code per commit, in general, your reviewers on the average should be able to capture as much as 80% of the defects in your code. So that's good enough as a trade-off. So here's what you can do actually using Git. We are able to actually calculate the average lines of code per commit per week for every person. So if you look at that graph on the right, what I have there is that for each of our engineer for every week, I have a way to monitor, what's the average lines of code that they're committing for that week. You can see, for example, that this person right here, I'm sorry if it's too small, this person is Anthony, is doing just fine, right? Everything is green, the lines of code are small. He's a good example, right? But look at this person right here, right? Bella and perhaps Janice right here seems to need a bit of help, right? You can see that the lines of code that they're committing seems to be quite large, right? And you can see also Dawson having the same problem, right? Without software engineering analytics, it's very difficult for us to actually see, what's going on. But with all this information, I can even give this information to the engineers and say, hey, here's the leaderboard. Feel free to use them as you like. And I can even talk to my engineering managers and say, oh, during your one-on-one, this could be a KPI that you can ask your engineers to try to achieve, right? If they're able to coach the younger engineers on how they can improve the quality of their code, not only will the company benefit, every other company that the junior will, join and actually work for later on will enjoy the same value that we are training them here. So we're creating a significant amount of value to the person and every single company that he will impact along the way. That's a significant amount of good that we can do for the person and also for society. Um, because we're at Google, at least Google DevFest, Google Cloud actually have this set of metrics as well. Many of you who are in backend, who are doing DevOps and SRE, you probably have read about this. But if this is your first time hearing this, this is something that's extremely important as well. And here's the reason why. Uh, Google Google actually acquired a company called Dora, which is a DevOps research I think association it was, and they did a study of I think over 2,000 different companies, ranging from a very small startup to gigantic multinational companies with more than 10,000 engineers, and they found that there are actually four major metrics that no matter the size of the company, so long as you uh, optimize for all these four metrics, it's a very good indicator of a high performing software engineering organization. I'm going to go through them one by one and I'll try to explain to them as briefly as I could. But of course, you can access all this information online. And if you want further details, there's a book called Accelerate, which was published, I think, in 2019, that goes into further depth on these concepts. Here's number one. There's a metrics called the change failure rate, which is the amount of errors or the amount of hot fixes that you create after a release, right? In general, you don't want to do hot fixes. Hot fixes are generally bad, right? It's because some critical bug is found in your code, and that's why you have to patch it, right? So on the average, for every 6 to 7 release, you want to have the a good number is that for every 6 to 7 release, you have one hotfix. If you can have less hotfixes than that, that's even better. But that's the golden number. Every 6 to 7 release, one hotfix. What you're seeing here is an actual data from Hubble. And you can see that we are doing really bad, right? The 6 to 7 release per one hotfix for every 6 to 7 release equates to 0.15 in this y-axis right there. We are significantly higher than that, which is not good at all. So as you can see, over several months, things are going down, but it's not good enough. Without software engineering analytics, there's no way for us to know this. Now that we are seeing this, we can monitor this. I can show it to the engineer and say, hey, we have to do better as an organization. If we don't do this as good as we can, then you will suffer, I will suffer, everyone will suffer. Nobody will win. Here's another one. There's this concept called mean time to resolve, which is the average amount of time it takes for you to resolve an issue. So here's how you can measure it. In whenever you tag a release, I suppose many of you probably have been tagging your releases, right? Whenever you tag a release, you can actually use semantic versioning to identify whether a release is is actually a release, or is it a hotfix? For those of you who don't know what semantic versioning is, it's simply this. You might have seen a lot of software that are versioned 1.2.0, 1.2.1, 2.1.0. So that's semantic versioning. You have a major version, a minor version, and then a patch. So how we are doing it at Hubble is that for every release or intended release, it's actually tagged as 0. It ends with 0. So it's a 2.1.0, 2.2.0. And every hotfix is actually a number towards the right, which is the patch, right? 2.1.1, 2.1.2, yada yada. So with those information, I can actually collect those information, take a step back, and find out how much time it takes for me to create a hotfix for every release, for every 0, for every semantic version that ends with 0. How many time does it take for me? How much time does it take for me to create a version 0.1, a version 0.2? So what we're seeing here is that we are actually not doing very well as a company. I have to have as less amount of number there as possible. Here's a good thing to note as well. Sometimes in our friend at Apple, it takes them about 1 or 2 days to actually review your iOS app before you can publish to the App Store. So this is actually affecting our numbers. So what we have decided is that whenever an issue is found in production that's a showstopper, it should take us only 1 day to fix it. Anything more than that, that's not good. So for us, we set a service level objective for ourselves to actually fix any issue within 1 day. Here's another one, again from the DORA metrics. It's called the change lead time, which is the amount of time it takes for your commit to actually reach production. This one is very important. Many of you who has been writing code for a while have probably noticed that there are some code that you have written somewhere in the past that never hit production, even if it's good, even if it's good for the product, good for the customers. So we want to measure this as well, because the moment we start measuring, we can now think about improving it. It's very difficult to improve something that you don't measure. So what you're seeing here in the graph is that, okay, a bit of a step back. In Hubble, we actually release every week. So a good change lead time is actually 7 days, which is a week. So if we go beyond 7 days, it means that we are slowing down. It means that we missed a release. That's why we go beyond 7 days. If we are less than 7 days, it means that there's a lot of hot fixes. That's why the change lead time is short. So for us, the golden number is 7 days. So we need to hit 7 days. And as you can see from the graph here, we are not doing very well. There's a lot of hot fixes. And you can see that because the blue and the green line is actually below 7. It means there's a lot of hot fix. And here's the last thing. There's this thing called deployment frequency, which is the frequency of your deployment. In general, a highly successful engineering organization actually deploys on demand. For Hubble, we actually decide that, okay, we deploy once a week. Of course, for the backend, you can deploy anytime, but for frontend and mobile, because they have to pass through QA and so forth, it takes about a week. So what you're seeing here is actually the clients, meaning the apps and the mobile app and the web. So again, we want one release per week, one deployment per week, at least for the clients. And if it happens more often than one per week, it means that there's a lot of hot fixes. If it happens less than one, it means that we are not delivering on time. We missed the release. So again, it's important for me to measure that as well. And this one is very easy to track. I just need to count the number of tags that were created per week, and that becomes the deployment frequency. Now, enough of the analytics. Let me actually show you how you can do this on Google Cloud. Of course, if you have any questions, feel free to throw it in the live chat. I'll do my best to answer if I can. So here's the way we build our analytics stack, our business intelligence stack. We are using Python as our programming language. And we are using Airflow. Let me talk about Google Cloud first. You can use Google Cloud, for example, Google Cloud Storage. And here's the pipeline. So first, you actually create a Python request for a bunch of APIs available from GitHub, and collect those information using Python Panda. For some of you who are not using Python, Panda is simply a library for you to parse a CSV, an Excel file, or a database query. You can parse it to become a 2D array that you can actually process. So you can use a Panda to parse the output of the REST API and actually send it all the way to Google Cloud Storage as a CSV. This is important because we want to do data load. A data load, what that means is that you don't load the whole history of your GitLab information into your Google Cloud Storage. Of course, you do it the first time, right? When you want to do a first load, right? Then you load everything. And then what we do is that every day, perhaps at 12 midnight, you pull a new set of data, let's say from yesterday to today. And then for midnight tomorrow, you pull today to tomorrow. So you do that every day around the midnight. And eventually you create a cadence of this system actually doing that for you. So now that it's in Google Cloud Storage, we can actually send it to Google BigQuery, whereby Google BigQuery, as you might know, it's a columnar database that's optimized for analytics. So you can send those information to Google BigQuery, and we are using Metabase as our business intelligence tool. Of course, you can use other solutions such as Looker, for example. You can use Microsoft Power BI. You can use Data Studio, for example, if you like. There's Holistics out there. You can use all sorts of solutions for your BI. We are using Metabase because we are cheap, it's free, that's why we are using it. And if you see this thing right here, it's called Apache Airflow. That's the one that orchestrates the ingestion of the data from GitHub to Google Cloud Storage to Google BigQuery. And here's, if you haven't done data engineering before, this is normally what happens in data engineering. So you use a directed acyclical graph. What it does is simply, it's just a parallelization of task. So what we are doing here is, it might look very, very complex, but trust me, it's very easy. So the idea here is that we are simply calling a bunch of APIs. And if you're doing reactive programming, for example, you know that as long as one API doesn't depend on the other, you can actually run them in parallel, right? So we are simply saying, we are starting here, and then you can parallelize all these API calls and save them to your Google Cloud Storage. And then you can call this API, save those information to Cloud Storage. Then you continue, and then you eventually finish the entire task. For us, it takes about maybe about 15 minutes, and then the whole pipeline is done. It might look complex, but it's actually very easy. Um, so with this in mind, I'm probably going to skip this. However, because this video is actually recorded, you can actually go back and see how it looks like. As simple as it is, we just want to share with you that this is the data model. So what we did was we tried to identify from GitLab's API response, what's the model looking like, and we actually model our tables based on that. I know it's quite small, so it's probably not very easy to read. But then, of course, if you rewatch the recording again, you can definitely zoom in. I'm going to skip this one, but it could be good for you to see how we sort of modeled our tables. There's one challenge that I would like to share with you all, actually, if you plan to do this, because you will surely run into this. So if you use Git before, and I'm sorry, I think most of us use Git, right? But remember that when you set Git up the first time in your machine, it will actually ask you for your email and your name. Interestingly, whenever you commit your code to your repository, either it's GitHub, Bitbucket, GitLab, yada yada, uh, you can actually commit code uh, even if the one who wrote the code is not from your company. And here's the reason why. Um, you can have a random text for your name and email because the one that actually pushes the commit to your repository could be a totally different person than the one who wrote the code. So we found a scenario whereby our engineers are using multiple machines to write their code, to commit, and stuff like that. And sometimes they will put their name as John, and they put their email as John at mycompany.com. And in another machine, he will name himself his full name, John Wick. And so it becomes confusing for us because now it becomes difficult for us to attribute different commits by the same person to the same person, because they have different supposedly unique keys, which is the name and the email combination. So in order for us to resolve this, we actually have a lookup table. We created a lookup table to say that, okay, if you see this combination of name and email, it means it's this person. This is something that's not part of GitLab, and we have to do it manually. The reason why we have to do it manually is because once in a while, people will commit their code somewhere, from a different machine which we don't know of, and then a new data surfaces, and now we are not able to track. But because these things happen few and far in between, we would actually do it perhaps once a month, once every 2 months. So it's not actually as difficult. But this could be one of the gotchas if you try to implement this. For the next two slides, it's actually just a list of API calls that you can use. Of course, all these information are very well documented in GitLab's API documentation. So this is just to kind of share with you some of the APIs that we have used for this to solve this problem. So that's pretty much it, actually. Thank you so much for your time. Thank you for listening. I'm very glad to be here. And if you have any questions, I'll be happy to take it.